Hello all. Today we will work on section 16.4 and if possible 16.5. What is 16.4 about? 16.4, section 16.4 is on Green's theorem. Now, before we start with the theorem, let's define or take a look first on one word orientation of a closed curve definition. The orientation of a closed curve. Now let C be a curve enclosing region C. Region D, I'm sorry. Okay, so this C here is a curve that is enclosing region D. Now, the orientation of that curve C is positive if the traversal along C has region D on its left. Maybe I say left-hand side. Okay, now this definition is more about convention. It's not really about, it has to be like this, but to make the, how to say that, let's go back to this. Like, let's say this curve C, and then you have D. There are two possible ways to travel along this C. One way is counterclockwise, right? Another way is clockwise. Okay, now to make it uniform, then those mathematicians came before us, make a decision. Let's just make it this way, that we will always go counterclockwise. Okay, assuming the domain is on the left-hand side. So let's say Thomas is actually standing here. Okay, and how do we know that I'm supposed to go to clockwise or counterclockwise? Then you see where the region D located. Okay, so I will travel this way if my left-hand side is the one touching the domain. Okay, now that's what it means to say that you travel along curve C with region D on your left-hand side. Okay, now of course the consequence then, our textbook, the way our textbook and many textbooks describe that, that C traverses counterclockwise in relation to region D. Okay, then maybe I write it down here. Consequently, as many textbooks describe, C traverses counterclockwise. Okay, it is more about the position relative to D though. In other words, suppose I have a curve C and the region D that we are talking about is the one looks like this, right? The region is actually the one outside of that white one. Then the positive orientation actually refers to this one if you travel this way, because then this is the direction you travel such that the corresponding region is on the left hand side. Okay. Now let's go on further. Once we define the orientation of a curve, then we can go on with Green's theorem. Green's theorem say the following. Let C be a positively oriented piecewise smooth and simple and closed curve. Enclosing D, region D. So before I go on, so I think if you can look at the C that we have above there, it's positively oriented. Piecewise smooth means it actually moves the first derivative of the RT, if you parameterize that, is actually smooth and not equals to 0 except at some countable number of points. So let's say it looks like this. Okay, so when you do R prime T, for example, along this path, you're okay except at this one point, but then you can continue here, except at this one point, then you can continue further, and it forms a closed circle. Simple means it doesn't intersect itself, right? Remember the simple and non-simple. Closed curve means the initial point of the curve the same to the terminal point of the curve. Okay, something really, really nice. Just put it that way. Okay, now then N, let vector field F with XY component, only 2 dimension, be vector PQ, where P and Q are functions of X and Y. Okay, let this vector field be a vector field with continuous partial derivative. Which means you can do the dou P dou X, dou P dou Y, dou Q dou X, dou Q dou Y. On an open region containing D. Think of it this way, that this vector field has continuous partial derivative not only on D, not only on D, okay, but also including the boundary, okay, and also including a bit over the boundary, so that however small, so that even if you choose a point on the boundary, okay, there must be a circle fully contained in that open region in which the vector field has continuous partial derivative. This way of defining it guarantees that the vector field F has continuous partial derivative everywhere on D, including the including the boundaries, which is curve C, okay, from every direction. Okay, so if you choose a point on C, you can find the vector field has continuous partial derivative in any direction to that point. Okay, because you have a circle in which you have you have an open region. You have a circle in which the vector field is still have continuous partial derivative. Okay, yeah. This way we guarantees that the vector field behave very well, not only on D but also on the boundary. Okay, and slightly a bit over the boundary. Now let's go on. Then integral over closed curve C, I think this is the first time we see that notation. This is just a regular line integral, but we emphasize with that circle around the integral sign to emphasize that this is actually a closed curve. Okay, so integral, the line integral over closed curve C of f dot dr is equal to double integral over D of q sub x minus p sub y dA. Now, we usually say because C encloses D, basically C is the boundary of D, right? We can say C is the boundary of D. So C equals to dou of region D. Okay, now this is what Green's theorem actually says. Let's take a look on one or two examples. I will just pick questions from the book. Okay, it's just to clarify what this theorem about and how to use it. Okay, let me pick example 1 from our textbook. Give me a second. I think I start losing my voice. I'm sorry. Example 1. Evaluate this integral where C is a triangular curve consisting line segment. Let me do this first. Consisting line segment from 0, 0 to 1, 0, from 1, 0 to 0, 1, and then from 0, 1 to 0, 0. Okay, so that's our C, right? Okay, notice that the C, that C is the boundary of region D, if this is our region D here. Okay, now that integral over closed curve C of x to the 4th dx plus xy dy, this is equal to integral over closed curve of C of x to the 4th xy dot dr. Take a look. I basically re-express this integral as our theorem. Okay, in other words, our vector field F is x to the fourth xy. That's our PQ, right? Okay, that's our PQ. Move that a little bit to the left. This is PQ. Okay, now then according to this theorem, it says that Q sub x dou Q dou x equals to y dou P dou y equals to 0, huh? Okay, so by Green's theorem, that integral becomes double integral over D, the region that closed curve C encloses, times of the integrand y minus 0 dA. Okay, and then we rewrite that region D. We be more specific with the double integral from 0 to 1, and then integral from 0 to 1 minus x y dy dx. Is it right? Which is equal to integral from 0 to 1, 1/2 1 minus x squared dx. We integrate again. I think I will do a little substitution here. Integral from 0 to 1 with 1/2. This is u squared du. Okay, which is 1/6, which is equals to 1/6. Okay. Now, this theorem basically say instead of you doing integral over closed curve C to be integral of C1 plus integral of C2 plus integral of C3, instead of doing it that way, if it happens to be a closed curve, then we can just take a look on the double integral over the region it encloses. Okay, notice that if you break it up into C1, C2, C3, then for every path you need to parameterize the path, right? And then you need to reinterpret what x and y are in those segments. I show you what I meant. Okay, so suppose you do it long way without using Green's theorem. Then, for example, C1 will be managed by R1t t comma 0, right? The t will be from 0 to 1. So dr1 of t will be 1 comma 0. Okay, so integral over c1 of x to the 4th dx plus xy dy, that is equals to integral from 0 to 1. X to the 4th will be t to the 4th times dt plus xy dy, which is 0. Okay, 0 dy, 0 dt. But this is basically 1/5, equals to 1/5, right? And then after that you move on to C2, and then after that you move on to C3, and after you're done with all those three integrals, then you need to add them. You see, that's so much trouble to do, right? So instead of doing those three paths, we look at only one region D. Okay, let's say example 2. I'm not really happy with this. Maybe example 2 help us to be more clear what this theorem is about. So we have integral over closed curves this, but then C is the circle with radius 3. So this is the C. Okay, this is the C. let's make it this orientation, because this is the orientation of C, then the D must be the region on the left-hand side of that C. Okay? Now then, notice that the vector field F is 3y minus e to the sine x, comma, 7x plus square root of y to the 4th plus 1. Now, q sub x will be 7, p sub y equals to 3. Right? So integral over closed curve of C of that 3y minus e to the sine x, comma, 7x plus square root of y to the 4th plus 1 dr. This is equals to, according to Green's theorem, is equals to double integral over region D, which is the disk width radius 3 of q sub x minus p sub y dA. Okay, but that's basically 4 times the area of D, which is 4 times 9 pi. That's 36 pi. Okay. Now that's the nice thing about this Green's theorem. Now, more things to say. If you think about it, then the area of D, note that the area of D of region D is equal to, we usually rewrite it this way. We rewrite this as double integral over D of 1 dA. Is it right? Okay. Now, which, if you think about it, you can see this implies, you can kind of manage, think of it as like dou q dou x minus dou p dou y. You set that to be 1. The 1 here. Maybe I use different color. That's the one you set to be 1. Now, this difference may become 1 for a couple reasons, actually a lot of ways, but one way is to say that dou q dou x equals to 1, but dou p dou y equals to 0. That will make it, right? Okay, but if that's the case, it means p equals to 0, q equals to x, right? Which by Green's theorems, this is actually integral over closed curve of the boundary of region D of of p dx plus q dy. Right? Okay, which we can just write in integral of a closed curve of boundary of D of x dy. In other words, one way to compute the area of D is to compute x dy of whatever, using the one of the example we have above. You compute x dy over this closed curve of the boundary of D, which is C. Okay. Another way, of course, we can say, oh, you know what, Thomas, when I look at this expression here, can I make the d dou q dou x to be 0? Dou q dou x to be 0. But my dou p dou y to be -1. Of course, that will work. Okay, that will make p equals to -y and q equals to 0. Right? And the area of region D, therefore, may be expressed as -1 integral, line integral over closed curve C of negative y dx. Okay. Now, of course, another way is you set dou q dou x equals to some number between some number, let's say 1/2, and dou p dou y as negative 1/2. That will give us p equals to negative 1/2 y, and q will be 1/2 x. And this line integral, therefore, line integral over closed curve C now becomes negative 1/2 y dx plus 1/2 x dy. Okay, which we can write as integral over closed curve C of hold on. Yeah, that will be let me factor 1/2 out, and then x dy minus y dx. Okay, even though I prefer to use the notation we have above there, because it's basically saying that this is 1/2 integral over closed curve of C of negative y comma x dot dr. Okay, if we write that as the vector field notation. Okay. Let's see example 3. Example 3 in our textbook actually went over an example how to compute the area of a region using the curve that encloses it. Sorry. Where am I? I'm sorry. Where I suddenly jump here? I want to go here. Oops. I happen to copy the solution also. Give me a second. So in example 3, find the area enclosed by this ellipse. So you have an ellipse with center at origin, and the horizontal vertices are a, 0, negative a, 0, and b, the vertical vertices are 0b, 0, negative b. So let's say that's the ellipse. Okay, now if you want to find the area of the region it encloses, then parameterize your curve that encloses that in a way such that the region D is on the left hand side of that curve. Okay, so instead of like doing the double integral to find the area of that ellipse, what we can do is we parameterize that ellipse. Okay, so you see that I can say C is parameterized by RT, where the x component is a cosine t and the y component is b sine t. How do you get that, Thomas? Think of that as a circle. But then you stretch that horizontally by a factor of a. That's why you put that a here, and stretch that vertically by a factor of b. Okay. Now then, from here we do, okay, then what is the r prime t? Or r prime t is a, negative a sine t, b cosine t. Okay, so the area of that ellipse is equal to integral over closed curve of C of negative y comma x dot dr. Okay, which is, if we parameterize that, that's integral from 0 to 2 pi. The y will be negative b sine t. The x will be a cosine t dot negative a sine t b cosine t dt. Okay, and that's integral from 0 to 2 pi of ab sine squared t plus ab cosine squared t. You see how nice it is, right? They end up being just ab. Integral over from 0 to 2 pi of ab dt. Of course, this is ab times 2 pi. Okay. Now we have three different formulas though. How do we know which formulas we can use, Thomas? You can use this formula or this formula or this formula for the area of region D. Now, I use the third formula because it happens that the derivative and the dr and the combination of negative y comma x happens to give us a nice expression like this. Okay, now that's for example 3. From here, I will go on with a slightly more complicated notion. Now, suppose our region D is a union of simple region. Maybe to be more precise, our region D is not simple, but we can see that as union of simple regions. Think of it, for example, this kind of region here. Now, this is not simple. Remember, the definition of a simple region is when you choose 2 points on that region, then however you draw a path, a closed path maybe, from one point to another point, okay, it will not enclose something outside of that region. Okay, now in this case, you see that I have a closed curve. Okay, I have a closed curve that does not include a closed curve that encloses a region not in D. Okay, so this region is not simple. However, we can, even though this region is not simple, we can break this region up in a way such that it looks like a union of simple regions. Okay, so you break it up into this kind of region here. Let's say this is the first region. Okay, and this is the second region. Let me use different color. Maybe I use the green one. Okay, now notice that we will break, it's basically this kind of path. We end up with this kind of path. This is one of the region here, the green region, we call that, just for now, and the red region. The red region encloses by this red path here, right? Okay, notice that the original region D, the original region D, oops, sorry, the original region D has this path. Okay, there are two paths, not intersecting paths on the boundary of D. Right now, the problem is these two paths are not connected though. Okay, now what we can do is now we see it this way. We see it like, oh, okay, this is the first path. Okay, and this is the second path. Now, notice that the paths along, maybe what color I want to use, on this part here, they cancel each other. Okay, it's the same path but opposite direction, right? So when you add them, they will cancel each other. Does it make sense? Okay, now what I'm saying is like original region D now can be rewritten as the domain of D1 and D2. Okay, with region D1 is enclosed by C1, region D2 is enclosed by C2. Okay, so region D is equal to region D1 union region D2. Okay, therefore the boundary of D is now equals to the boundary of region D1 union the boundary of region D2. Okay, now for that reason, therefore, double integral over region D of q sub x minus p sub y dA will be double integral over D1 of the same expression plus double integral over D2 of the same expression. But for each of them, because you have a closed curve enveloping that region D1 and D2, then we can write this double integral over D1 as integral over closed curve C1 of f dot dr plus integral over closed curve C2 of f dot dr. Okay, now let's take a look on example 4. This one, I like this example, by the way. Example 4 and example 5. So in example 4, we have this question here. Evaluate this line integral over closed curve C of this vector field, where C is the boundary of semi-annular region, with upper half of after half plane between circles with radius 1 and circles with radius 2. So that's what it looks like. Okay, now the thing is, like, if you look at the boundary, there are actually 4 paths, and therefore if you really want to do this the line integrals, then you need to do 4 type of parameterizations, 4 kind of integrals, and then you need to add the total you need to add those integrals. Okay, now instead of doing that, instead of doing this of y squared dx plus 3xy dy, instead of doing that, what we can do, we rewrite that as double integral over region D. Okay, now take a look, the vector field F, which is PQ, is the p is y squared because that's the one correspond to dx, right? And the q is 3xy because that's the one correspond to dy. Okay, so q sub x will be 3y. Okay, p sub y equals to 2y. Okay, so the double integral now becomes the 3y minus 2y dA, which is double integral over d of y dA. But that double integral can be easily computed by integral using polar. Integral from 0 to 2 pi. I'm sorry, integral from 0 to pi, not 2 pi. Integral from 0 to pi, integral from 1 to 2 of y, which is r sine theta, r dr d theta. And notice that I hope you remember this is a double integral over quote-unquote rectangular domain. You see the domain? I know it's actually in polar, but if you look at that, is rectangular domain, and the integrand is separable, right? Just to remind you what we have from chapter 15. So we can rewrite this as integral from 0 to pi of sine theta d theta, and then times integral from 1 to 2 of r squared dr. This will be 2, this will be 1/3. I'm sorry, yeah, 1/3 of 2 squared minus 1 squared, which is just 2. Oh, I'm sorry. No, should be cube here. So that's 2 times 8 minus 1, 7 over 3. That's 14 over 3. I'm sorry. I almost counted incorrectly. Okay. Now, that's for example 4. So think of it this way though. This Green's theorem here does not say that every time you do line integrals, closed curve line integral, you always have to rewrite it this way. No. In fact, you can also go backward. Okay. So from line integral over closed curve, you rewrite that as double integral, or double integral, you rewrite that as line integral over closed curve C. Okay, it's actually 2 directions instead of only one. Sometimes one of them is easier to do compared to the other one. Now, I would like to go over example 5 because I remember when I did when I took the course in complex analysis, we happened to bump into one big theorem that has something to do with what we have in example 5 here. Okay, suppose we have a vector field F equals to negative y over x squared plus y squared and x over x squared plus y squared. Okay, show that integral over any closed curve C of f dot dr is equals to 2 pi for any C, encloses origin. Or any C encloses the origin. Okay, now let's see what is the issue first. The issue is this vector field is actually not defined, not continuous at origin. Okay, this is not continuous at origin. It's not defined at origin. Okay, now, but at the same time, we are talking about any type of closed curve C. Okay, what it says is, well, can you then compute the integral of a closed curve C of that vector field for any closed curve C that encloses origin. Okay, now the trick is as follows. We will draw a circle, very small circle maybe, or any circle with radius r fully inside of that C. Okay, and it will run in the following way. Okay, the C will travel, of course, will travel this way. Okay, and then we will draw this slit here. I do this random slit actually. So imagine if I come from here, I go to the C, go around that, and when I get very, very close to that, I go back here. Okay, and then I travel this way. Okay, call this gamma 1, gamma 2, gamma 3. Notice that gamma 1 is opposite of gamma 2, right? Okay, and gamma is basically the union of gamma 1 union gamma 2 union gamma 3. So it's good. Okay, now consider the curve C union gamma. Okay, it encloses the region inside C but outside of that circle. Circle that is enclosed by gamma. Okay, now, but if you look at that region, let me mark the region. The region is basically this region here, the region that does not include that circle but inside C. Okay, now notice that the region inside that closed curve C but outside of that gamma actually a region that is in which the function is continuous, right? In other words, we can apply Green's theorem there. Okay, let's say this way: integral over closed curve of C union gamma of f dot dr. My closed curve looks ugly. Of f dot dr is equal to double integral over region inside C but outside gamma. Right? Of, now we can do the q sub x and p sub y. Okay, let's q sub x minus p sub y of dA, where my q is x over x squared plus y squared, and my p is negative y over x squared plus y squared. If I do the partial respect to x, the q, partial of q respect to x, then that will be, on the top I will get x squared plus y squared minus x times 2x. That is negative x squared plus y squared over x squared plus y squared being squared. While my dou p dou y is negative of x squared plus y squared minus negative y times 2y over x squared plus y squared being squared. This is just algebra, by the way. Okay, and I will end up with x squared minus y squared over x squared plus y squared being squared. Now, then what is dou q dou x plus minus dou p dou y? This guy minus this guy give me negative 2x squared plus, hold on, q sub x minus p sub y. So this minus this minus this. Do I actually compute that correctly? Oh, I'm subtracting. What am I doing? I'm subtracting. Hold on. Q sub x is this. X minus x times x. That's it. And then, I'm sorry, I kind of like a bit lost. The derivative with respect to y, so that's negative this minus this times that. Oh, it becomes plus. Oh, it's like this. I forgot this notation. And oh, then if I subtract, they cancel each other. Then it becomes 0. Huh? Okay. In other words, integral over closed curve of C union gamma, not gamma 2. I'm sorry, gamma of f dot dr equals to 0. Okay, but at the same time though, integral over closed curve C union gamma is integral over closed curve C f dot dr plus integral over gamma 1, right, of f dot dr plus integral over gamma 2 of f dot dr plus integral over gamma 3 of f dot dr. Compare that with the graph here. Now notice that gamma 1 and gamma 2 is actually canceling each other, right? Because they are exactly the same path but opposite of each other. I can write it this way. So this is integral over closed curve C of f dot dr plus integral over gamma 1 of f dot dr plus becomes minus of gamma 1 of f dot dr. Again, because those gamma 1 and gamma 2 are the same path with opposite direction, then the integrals must be canceling each other. Okay? Now, but notice that notice that integral over closed curve C of f dot dr, the orientation there is positive, right? Okay, and gamma 3 is also actually negative, huh? Right? Take a look. Gamma 3's orientation looks like this, right? Okay, let's reverse the direction. Okay, let's reverse the direction. This is gamma 3, right? Okay, now if I write that in as a closed curve, that's minus integral over positive counterclockwise orientation for gamma 3 of f dot dr. You will see that integral of any closed curve C, including the origin of f dot dr, must be equals to integral over positively oriented counterclockwise direction of gamma 3, any circle inside the curve C containing the origin. Okay, but this is integral from 0 to 2 pi of, let's parameterize that gamma 3. That's gamma 3 is parameterized by a very small radius a cosine t, a sine t. Okay, t is from 0 to 2 pi. Okay, what is the f? F is negative y over, let's take a look, what is f again? Yeah, negative y over r x squared plus y squared, comma, the q is x over x squared plus y squared, x over x squared plus y squared, dot dr. But this gives us integral over 0 to a of a squared sine squared t over a squared plus a squared cosine squared t over a squared dt. Now you will see the integrand is basically 1, and this is equals to 2 pi. Okay, which, if you think about it, it's basically saying the following. Suppose you have a closed curve enclosing the origin. The integral over closed curve including the origin is the same to the integral of any circle inside that closed curve C, including the origin. As if you can deform this closed curve C into any circle containing origin fully inside that closed curve C. Okay, now in complex analysis, there's something called deformation theorem. Basically, you can deform the path. Okay, you basically move all this path here. Okay, you move this path from the blue one becomes the red one. Okay, and it doesn't have to be, that path C doesn't have to be a nice one. That path C may be something fugly like this. Okay, why you can deform that to the circle with the red circle, the path gamma? Well, because between any closed curve C to that gamma, the vector field is continuous. Okay, and therefore we are able to deform it that way. And that's the case later on in complex analysis. I try to give you a preview, a very early preview of what happened if later on you take a course in complex analysis. Okay, now I'm basically done with this section, but of course we can never be happy if we don't do some examples, right? So let's attack some problems from our textbook. I will first take question number 4 from our textbook. Give me a second, I copy paste that question. We have integral over closed curve C, where C consists of the arc of parabola from 0, 0 to 1, 1. The line segment from 1, 1 to 0, 1. And then from 0, 1 to 0, 0. So this is the path. Okay, integral over closed curve C of x squared y squared comma xy dot dr. Okay, now notice that that closed curve C encloses region D, right? That is equals to double integral over region D of q sub x minus p sub y dA. Okay, which is equal to how to integrate that. I think I will integrate integral from 0 to 1 and then integral this will be dy dx. So this is from 0 to square root of y of 1 minus 2x squared y. Can you follow me so far? I hope I don't make miscomputation though. Is it easier to integrate it that way? Or instead I will integrate from 0 to 1 and then from x squared to 1 of 1 minus 2x squared y dy dx. I think this is easier. Yeah, this is equals to integral from 0 to 1 of 1 minus 2x squared times 1 minus x squared dx. Anything from there, I think you can easily integrate that. Integral from 0 to 1 of 1 minus 3x squared plus 2x to the 4th dx. That is 1 minus 1 plus 2/5. That's 2/5. Okay, this one is harder to do. I think it's harder to do. Okay, so you see the question again is actually integral, line integral over closed curve, but then I reinterpret that into double integral over the domain D. Wait, I think I make a mistake. This is why the integral of that. What am I doing? I'm sorry. So, no, this is not correct. That's not correct. I feel strange earlier. Yeah, I need to correct it. So that's equals to 1/2 y squared from x squared to 1 dx. That's 1 minus 2x squared, 1/2, 1 minus x to the 4th dx. So that's 1/2 integral from 0 to 1 of 1 minus 2x squared minus x to the 4th plus 2x to the 6th dx. Yeah, then you compute it from there. Okay. Suppose I try to compute that using what we have there. Let's try this one. Integral from 0 to 1 of x minus 2/3 x cubed y from 0 to square root of y dy. So that will be integral from 0 to 1 of square root of y minus 2 over 3y square root of y times y dy. So y to the 3/2 minus 2/3 y to the 5/2 dy. That is 2/5 minus 2/3 times 2/7. I hope I get the same result. Why I feel like I don't get the same result right now? So 2 over 5 minus 4 over 21. 42 minus 20 over 105. That's 22 over 105. Let's see what do I have here. The LCD is 105. So this is 105 minus 70 minus 21 plus 30. What is this? 35 plus 21 plus 30. 65, 44. Oh yeah, that's the same. This is just integrating, right? So, okay, both of them happen to be doable the same way. Okay, that's for number 4. I happen to do it with 2 different ways. But my point of this exercise is really that when we try to compute this integral over closed curve, we basically reinterpret that using Green's theorem. Okay, and we compute the double integral instead. Okay, that's for number 4. Let's see more. Number 8. Number 8, we have this integral. As integral over closed curve C of y to the 4th 2xy cubed dot dr. Okay, that is equals to double integral over d, which is the ellipse, okay, of q sub x minus p sub y dA. Is it okay? And then this is double integral over d of negative 2y cubed dA. How to integrate that? This is x squared over 2 plus y squared over 1 equals to 1. So it looks like this. Oh, but this is an odd function, huh? Right? Let's see. This is integral from negative radical 2 to radical 2, right? And then integral of, that's if I solve for y. Y squared equals to 1 minus x squared over 2. So this will be negative square root of 2 minus x squared over 2 up to square root of 2 minus x squared over 2 negative 2y cubed dy dx. Okay, but you will see, I believe, when you integrate that, you will see, because of the fact that this is an odd function over symmetric domain, then that will be 0. Okay, that will be integral negative radical 2 to radical 2 of 0 dx. That will be 0. Okay, that's for number 8. You know what? I think, can we just do it manually from here? Just to check if we do it right. Okay, so C will be parameterized by square root of 2 cosine t. This is out of curiosity. Sine t such that r prime t equals to negative square root of 2 sine t cosine t. So integral over closed curve C of that is integral from 0 to 2 pi of y to the 4th sine to the 4th t dx plus 2x y cubed dy. Am I missing something? 2x y cubed. Why I feel like I'm missing something. Yeah, why I feel like I'm missing something. X, Y. X, Y cubed. That's correct. What am I doing? This is equals to integral from 0 to 2 pi of negative square root of 2 sine to the 5th dt, t dt, which is an odd function, right? Plus, maybe I do the dt later on, plus 2 radical 2 sine cube t cosine square t dt, which is still an odd function, right? And you will see that's equals to 0. Now, I say odd function because then from 0 to 2 pi, the integral will be 0. Okay, the period is 2 pi. And it's well, you can just do it yourself then, a long way. We do expect this integration to be a long one. Okay, that's for number what? Number 4, number 8. Let's see the next one, number 12. The question is integral over closed curve C of f dot dr. So if we have that f, we want to compute integral over closed curve C of f dot dr. Okay, but if that's the f, then q sub x is 2x, p sub y will be 2y. Okay, C consists of the arc of the curve y equals to cosine x from negative pi over 2 comma 0 to 0 to pi over 2 comma 0. So it looks like this, the cosine part. And then the line segment from pi over 2 comma 0 to negative pi over 2 over 0. So it looks like this. And notice the orientation is negative, huh? In relation to this d here. Okay, so this is negative double integral over d of q sub x minus p sub y dA. Let's pull out the 2, and that's 0 to pi, and the radius will be, oh, actually no, this region here, I'm sorry, this region here is from negative 1 to 1. I try to polarize that, negative 1 to 1, and then 0 to cosine x. Of x minus y dy dx. Okay, so this is negative 2 integral negative 1 to 1 of xy minus 1/2 y squared from 0 to cosine x dx. That's negative 2 integral from negative 1 to 1 of x cosine x minus 1/2 cosine squared x dx. Wow, we need to do integration by parts, huh? Okay, but cosine x is an even function. Okay, so x cosine x is an odd function. Okay. Replace x by a negative x, right? Then you will see negative x cosine x, which means this is odd function. On the other hand, cosine squared x is an even function. Therefore, this will shoot out to 0 because the domain is symmetric, right? And we will have just simply integral from 2 times from 0 to 1 of cosine squared x dx. I'm sorry, this is negative pi over 2. Why? Who say that's 1? I think I'm tired, sorry. This is equals to integral from 0 to pi over 2 of 1 plus cosine 2x dx. This will be pi over 2. Okay, that's for number 12. Let's do number 18. Yeah, I think after this I need to take a break. Number 18. A particle starts at the point negative 2 comma 0, negative 2 comma 0, moving along x-axis to 2 comma 0. Let's mark it using this way. Then along the semicircle of y equals to square root of 4 minus x squared. So it's this to the starting point. Okay, notice that the orientation is positive in regards of this d. Right? So use Green's theorem to find the work done by the particle on this particle by force field F. The work is equals to integral over closed curve of C of the force field dot dr. okay, which is equals to double integral over domain D of q sub x minus p sub y. Okay, so that's integral negative 2 to 2. Why am I doing that? Just make it polar right away. I will rewrite that first. I will rewrite that first. Double integral over d. I take the 3 out. Double integral over d of x squared plus 1 dA. Okay, now that d can be expressed using polar 0 to pi and then 0 to 2 of r squared cosine squared theta plus 1 r dr d theta. Okay, so this is 3 integral 0 to pi and then r cubed, so that's 1/4 r to the 4th cosine squared theta plus 1/2 r squared, right? If I integrate with respect to r, so that will be 4 cosine squared theta plus 2 d theta. I can factor the 2 out. Integral 0 to pi of 2 cosine squared theta plus 1 d theta. So that will be 1 plus cosine 2 theta plus 1 d theta. But this goes to 0 though on the integral from 0 to pi. So that's 12 pi. I hope I don't make miscomputation. Yeah, okay. This for number 18. Let me do the last one, number 19. I usually don't do odd numbers, but I think the reason I do this is because I don't find other similar questions, or this question is just unique. Number 19. Use one of the formulas in 5 to find the area under one arc of cycloid. RT equals to t minus sine t 1 minus cosine t. I honestly don't remember what it looks like though. So when t equals to 0, I think it looks like this. Is it right? I honestly don't know though. Okay, one arc, which means the y goes back to 0. Okay, y equals to 0 is 1 minus cosine t. Okay, so t will be 0 or t equals to 2 pi, huh? It goes back to 2 pi. Okay, so that's the one cycle. That's the one cycle. I want to find the area here, right? Let's use this area. Area equals to double integral over d of dA, but then we will see that as integral over closed curve C. Our C will be this one and then this one, but that's negative orientation. Make it positive. let's use y dx. Y dx. Will that be okay? Yeah, make it I need to clarify about the orientation. Give me a second. The orientation of the curve here is non-negative orientation. Okay, but the formula itself, notice that the orientation is like this right now, of negative y dy, y dx. Okay, so now I want to make it positive orientation. When I make it positive orientation, which is counterclockwise, then the negative cancels. The y is 1 minus cosine t. And then the dx is 1 plus 1 minus cosine t also, dt. Okay. How do I compute this? I'm sorry, I'm very tired. I'm extremely tired right now. And the t will be from 0 to 2 pi. I already used t there. Yeah, basically you need to solve that. So for that one. Okay. This will go to 0. Cosine squared t is 1 plus cosine 2t over 2 dt. So that's another pi. That's the area under that. Okay, suggested homework from here will be from 11.4 will be number 1 to number 14, 22, and 24.